Hello and welcome back to Precalculus1. Not calculus, Precalculus. There we go. So today I am very excited because we get to do exponential growth, decay, mathematical modeling, word problems, all of the coolest things that we can learn in Precalc1. And it is my absolute favorite section because it is very applied, very useful, and it gives the base for technically every science out there, real and fake. So we're going to start by dealing with money first, then we'll deal with population, and we'll deal with history and all environmental sciences and a whole bunch of stuff. Probably won't do any of the fake ones, but at least we can get the real ones out of the way. All right. So let's take a look at what we are dealing with here. So we start with formula, which we are going to dress up into different outfits, right, as we move from concept to concept. So the main idea, the main formula for the whole lecture is to know y equals a e to the k x. That's our main equation we have seen before. It's exponential function, and it's the one that we are going to use to deal with a lot of this stuff. Now, we're also going to draw two graphs that will go together with this function. So this is our y-axis, this is our x-axis. And on the first one here, we are going to have this, which will go through value a. And this is what we will call growth, because you see that the function is increasing, right? It goes up to infinity. And we are going to say that happens when your k is positive. This k right here. The other graph will look like this. Will also go through a. And this is something we'll call decay for k less than 0. And that's our theory, right? Stuff that we need to know from before. And now we are going to jump into some calculations and see in which ways we can use this. Now you need to have your calculator handy. Anytime you calculate log and exponential, you should keep four non-zero decimals, right? We are going to talk about it every single time, but we need to be careful because exponential logarithmic functions pile up a lot of error as you go rounding from step to step. So the more you round, the more mistakes, right, you get. So the more error you accumulate. So we try to keep it at 4 decimals and gives us somewhat reasonable answers. Now, your final answers to word problems should use some common sense. If they're asking about population of people, and people are whole units, not parts of the units, hopefully you will not be providing decimal answers. If the answer is money, hopefully you will be giving only 2 decimal places because cents, right? 2 decimals. So, some common sense should be there. But some problems will say, use 2 decimals, use 3 decimals, or whatever. So you use as many as they want. That's my MATLAB. Otherwise, they will mark you wrong. All right, so now let's first get some of these basic calculations before. We need to know everything from previous 4 sections in order to be successful here. Obviously, we need to know the conversion formula so that we can deal with equations, because every word problem now will give us some form of this equation, and then we need to solve it by converting it into logarithmic equations. So conversion is something that is important, and what we have here is that a to the b equals c converts back and forth to log a of c equals b. So we will be going back and forth between these forms. All right. What we have seen before is the situation about money. Right? So what do we do here? Well, we had a problem before where we kept adding the interest, and we call that compounding interest, and we were able to compute the value that is collected because someone lent you money. So when you buy a big ticket item, a car, house, you take a loan of some kind that is, a larger loan, either to start a business or something. You might not have the cash to pay for it, so you have to borrow someone else's money, then you have to pay them interest. So the formula, we're going to have two different formulas here. One is going to be called compound interest, and the other one is going to be called continuous compounding. So for this situation, I'm going to write those two formulas where the amount you owe is equal to the principal times 1 plus r over n raised to the nt. So this is called compound interest formula. And I do a formula compound interest because over here on the other side of the wall, A equals PERT. This is continuous compounding. Please note that this is your old y equals a e to the kt formula, which I mentioned up there. It just has different letters, right, for variables, because we are going to have these variables as A is the amount, P, principal. That's the money that you borrow or money that you lend, depending which way transaction goes. R is rate. Rate is given in percent. We need decimal. Yeah, it's gonna be a bad day. There we go. We also need T as time. That's usually years. And then N is the number of compounds per year. So we have N equals 1, 2, 4. Can be anything. The most frequent one is N equals 12. That's yearly. N equals 52 called weekly. For whatever reason, N equals 360 for daily. Yeah, we know that year has 365 days, except when it has 366 days. But I guess banks operate on a 360 and say, you know, take 5 days off. All right, we're not going to compound. So this is, what is the compound? That's technically the day when they recompute your interest. And generally, for loans like a car or student loan or a credit card, right, they do that once every month when they recalculate the interest, right, and they adjust the payments. So how does the credit card work? Well, credit card really doesn't have this exponential form because you do calculation every month because you might be spending money in between. See, when you borrow money at one shot, right, then exponential functions will be in charge of calculating interest. But when you are continuously spending money, like all the time, borrowing money, because that's what you do every time you swipe a credit card, you borrow money from the bank. That's not your money, right? The credit card has your name on it, but that's just a name on the account. Every time you swipe a card to buy a $5 coffee at Starbucks or something, you actually borrow that money from the bank and then they charge you interest because they lend you money. It's a service. Only if you pay cash, obviously, or if you use your checking debit card, right, then it gets right out of your bank account and it's like working with the cash. Whether you're using your debit checking card, right, or you're using cash. But the credit card, that's not your money. That's the money that you borrow from the company and they slap interest on it. And then they send you a bill every month, right? And you need to pay it off. And if you're not paying it off, it starts accumulating, right? It's very simple principle. So credit cards always have, when you take a look in the back, right, of that paper when you're signing it, they always tell you what is the annual percentage rate, so APR, and you can get that one into monthly when you take APR and divide by 12. That should be common sense. Now, most of the credit cards that are used in regular transactions, right? You get the offer in the mail, you open it, generally 20 to 24, 25%. So I'll take 24% APR card, CC, credit card. That will work out to be 2% monthly. And we don't really need any kind of exponential function or anything. In this case, we just straight up calculate, right? So let's say you charge your credit card $700. So in May, right? So what happens in June? And let's do it this way. So in May, you charge your credit card this. What happens in June? Well, if you didn't make any payment, what you owe is going to be 700 times 1.02. So you have to add 2%, and you add 2% by simply multiplying by 0.02, 1.02. So 0.1 keeps $700 that you owe, and 0.2 adds 2%, right? So now you can quickly calculate that, because 2 times 700 is 14, right? So it's going to be $714 to $714, right? Would be on your. So that's how much you owe. So let's say you make a payment of $50. So now going into July, you owe $664. I was about 666, but no, it's 664. So that's how much you owe now, going into July. But hold on, in July, you are going to apply 2% again on it, right? So now you're going to have 664 times 1.02. It's going to give you that you owe $677.28, and then you are making another payment. Let's say you pay again $50. So now you owe in August $627.28. Now what happens in August? Times 1.02 again, right? So we don't really use exponential function for this, because in between these payments, you might have charged your card again, right? So you made a $50 payment, but some months you pay more, some months you pay less, some months you spend more, some months you spend less. So looking at this, it's not really good for exponential function, but at least now you know how to go through calculation to get those amounts. Now, if you take a look between the two numbers at any given point, you owe 700, then you owe 664. So what is the difference between the two? The difference is 36, right? But you paid 50. You see that there is a $14 in between, right? So that's $14 is the profit that they make, the company, the bank, right? And only $36 went out of 50 you paid, went towards paying off the card. And you can actually calculate, right, what percentage from the payment went to the interest by dividing 14 by 50. So these are some basic, right? It's 28%, right? So 28% of your payment went to the bank, and 72% went to paying off the debt. And you can do that calculation for every, right? You can make a nice Excel spreadsheet and compare, the money going into the month and the money coming out of the month, like these two, right? You can see the difference between those, and then you can figure out, right, the payment and figure out how much, right? So the credit cards are really, 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 really easy, and they don't require exponential. Well, the interest gets applied before or after the payment. Well, the interest gets applied before the payment, because they send you the bill where the interest is already included, right? But technically that's after the payment you made the next time. So it's like, yeah, before or after, it's the same concept. I hope you, right? If you study your credit card bill, you will see, right, if you take a look at every single line, you will see when they apply the interest. right? And they did the calculation. They can do calculation at any point. It doesn't really matter, right? You can figure out what your credit card is doing just by looking at the monthly statement, because there is exactly going to be one line in the monthly statement when they added interest, because it's monthly compounding, meaning computes the interest once a month, and they will be adding, right, this one. Now, what I want to, draw your attention to is obviously those store credit cards, which all of the retailers want you to open, right? You go there and they say, oh, look at this. Yeah, I really want to buy this $300 coat that I don't need because it's so cute, right? So, but it's $300. And what do? They say, well, if you open up our credit card, you get to save 10%, right? Oh, really? That's great, right? Because that saves me $30. That's like 6 coffees at Starbucks, the whole week worth of coffee. Yay, right? So you open the credit card to save $30. Great. Do you know what the interest on those is? Never less than 30, right? So 30% or 31%. I know a credit card, when I went to change my tires last year, they said, oh yes, you can save 10% if you open a credit card. I turned the paper around just to take a look, at the percent was 31%. I was like, nice. Yeah, I'm going to save. Because you guys, you've seen the percent-wise. I erased it, but I did show you that 28%, right, of this payment here, 28% went to the card company, right, of the payment, and only 72% went to the. So when you are opening a card that even has a bigger percentage, those numbers are worse. So more of each one of your payment will be going there. So, never open a store card. The general credit cards you must have to create the credit history. Otherwise, you won't be even able to get like a Verizon cell phone if you don't have credit history. You can get the swipe phones and stuff like that, but you can't use the burner, not the swipe, the burner phones. But you can't operate in society if you don't have credit history. But you do not want to build your credit history using store cards that are 30, 31, or even more percent. You're trying to get the cards that are, 20 to 24%, which are the regular standard cards like Visa, MasterCard, right, and all of those that are not store cards. All right, so that was a little bit about credit cards. Go ahead, study your bill, apply some of these, play with these. And so, no, you don't have to pay in full. You can just make payments, right? So if you spend $1,000 on a credit card, you can keep paying $50 until you pay it off. The problem is that people with when they go unchecked for spending, right, uncontrollable spending, they wreck credit card debt, right? And, that can be tens, even hundreds of thousands of dollars in debt because of impulse buying, right? I have some rules there is a very simple rule of what it is to be rich. It's a very simple rule. You should write it down. You say to be rich, just spend less than you earn. That's all. It doesn't matter if you're making $30,000 a year, $50,000 a year, or $3 million a year. If you are spending less you make, that's all it is. So, to pay, let's face it. If you are paying your credit card completely at the end of the month to avoid the interest, then why didn't you just buy, right? Why would you be borrowing money from the bank to buy something that you actually have money for to pay it at the end of the same month, right? So you either have the money or you don't have the money. Now, 99% of the people don't have the money. So they have to swipe the card, and these are all different different deals that they have. Sometimes you have 6 months no interest, and then the interest kicks in, and so on. That's for most of them just to get you to open the credit card, because they know that you will be using it past, right? And when you get relaxed, it gets piled up. I mean, that happens all the time. There is a reason why they're all swimming in money. They're swimming in money because we are collecting, effectively they collected 28% with that payment, right? Even though it looked like they charge, on a paper they charge 2%, right, interest on a month, but your payment, 28% of your payment went to the company. So think about it, right? They applied 2% interest, but 28% of your payment went to them. And 2 and 28% are really different numbers. So if you understand how this whole thing works, it's important to have this system, because a lot of people would never be able to afford a car, right? There will be no car loans. That's the next thing we're going to take a look at. There will be no school loans. There will be no loans of any kind, right? So interest as the institution must exist. But you cannot avoid interest unless you are very very disciplined with money, which again 99% of the people are not, which is why they're not rich. That's very, very simple argument, right? The only reason why people are not rich is because they are terrible with money. They don't know how to save. They spend everything, and they constantly spend money on stupid things. Like Starbucks coffee is an excellent example of wasting money. You can make your own damn coffee for 25 cents. You go there and you waste $5 or even worse, 6 or 7, right? So again, it works its own ways, but there are a lot of these things. So just take a look at your credit card statement, see when they applied the interest and so on. And if you have a deal for no interest, obviously you're trying to pay it off in there. If you have the money to pay something, why mess with the credit card then? Right? That's another thing. So a lot of things that you can. But let's take a look at these loans that would actually require of us to use our calculation, and that's going to be a car loan, or a student loan, or whatever. So they're all the same, and that's where we are going to use that compounding formula, and then we're also going to use E formula to calculate the absolute maximum of what we are for our payment. So we can use what we learned today to play with numbers before you go out to buy a car or to do something like that. So here is what we are going to do. Let's say price is, I don't know, $8,000, right? And we have no money, like zero, right? But we want to buy the $8,000 car. Now, $8,000 that you see online is the price that they don't want to negotiate, right? They say our absolutely lowest prices are listed online, so we cannot negotiate that price down. So take it or leave it. And now, that is actually not the final price. Because there is something is called tax. And also there are fees when you go to buy a car. There are fees for insurance and title and registration and a whole bunch of other little fees that are added in. So when you go there, your $8,000 is going to grow to maybe $10,000 of the price to drive the car out of their driveway when you're at the dealership, right? So it's never the price. So I'm just going to say we need to add capital 7% tax, hello New Jersey, and sale fees. Now I'm just going to say, I don't know how much sale fees are. So let's just put $700, right? $100 for insurance, $200 for, or $250 for, I don't know, $250 for the title, $70 for registration, right? So they're going to add up to, let's say, $700 there. So how much do I need to borrow, right? So we have $8,000 times 1.07, that this is add tax. So you keep the original price of 8,000 with a 1, and 0.07 is adding 7%, right? So that's 8,000 times 1.07 to give you 8,560. And then we add $700 of fees to get 9,260. This is the amount we need to finance because we don't have any money, we don't have down payment, we don't have, right? If you had the down payment of $2,000, then sure, you subtract $2,000 now. But we said we have no money, right? So we're walking at, right, with some credit score, right? And we just like this $8,000 car and we just want it, right? All right, so now we know that we need to borrow 9,260. And depending on your credit score, your percent could be anywhere from, 4%, let's say, and if you have the bad credit score, it can be 11, 12%, right? Depending on what your credit score is. Now, credit score obviously is calculated through, it's obtained and calculated when you are using and making payments on your credit cards. That's your credit history. The credit score is the numerical value of your credit history and how well you're doing with how many, how much you're borrowing, how much you're paying back, and there's a lot of factors that are you missing your payments, like all of that stuff impacts the credit score. So now here is where the problem begins. We need to borrow $9,260 at, let's say you have a good credit score, 4%, and you want to do that for 5 years. Let's do 3 years because, right, 3 years. Perfect. This is your principal. This is your rate. This is your time. And you just know that N is 12 because you are making monthly payments for the car. Monthly payments means they will be calculating interest 12 times a year, which means they're compounding, right? Compound interest, compounding 12 times a year, so n is 12, right? Now, that needs to be common sense, that 12 right there. Is it always 12? Well, unless it's 360, if they compound daily, which they're pretty much never do, well, they do it. There are quarterly paid taxes, so n is 4 and so on. There are situations when n is not 12, but generally if it's, not common sense that it's 12, it's mentioned in the text, having n equals blah blah compounds, right? So you will know. If they say weekly, it's 52, bi-weekly, 26, right? Because there are 26 bi-weeks every 2 weeks, right? And so on. Some people get paid bi-weekly, right? So they set up their payments bi-weekly, so they compound bi-weekly. It's just a lot of situations like that. All right, cool. Now I can compute the value that I owe back to the bank. It's principal. 1 plus 0.04 is my R divided by 12 raised to 12 times 3 years. So if you look at the formula, you will find all of these values, the R. Now R is converted to a decimal place. I can't really put 4% into the equation, right? I have to put its decimal equivalent, and that's 0.04. So now, 9260, 1 plus, and this is where we start figuring these things out, right? One by one calculate. So 0.04 divided by 12 is 0.003333. Remember how I said that we're going to use a 4 non-zero 4 non-zero right here. 4 non-zero numbers. So we don't care about this. We only care that there are 4 right there. That should give us some value. Let me just see. If you have 3,000... the mortgage doesn't work this way. I will mention it after the problem, so you'll have to. Let's just wait with the question on the mortgage with the 300,000. I see it there. All right, so now we go plow through these calculations. So we will add 1 to this number, right? So that's going to give us nice. Easy calculation, right? 1.003333 raised to 36. So now we're going to raise this to a 36th power and multiply by 9260. And the amount you owe is $10,438.54. By the way, calculators will round differently. So as long as you're in a ballpark of this, cents ballpark, you can get $20,000. As long as you are in this ballpark here, and as long as there is enough common sense to put 2 decimals for cents, we're in good terms, all right? This is how much you owe back to the bank. So you walked in to buy $8,000 car with nothing for down payment, right? And this is how much you have to give back. Now, what's the monthly payment? Well, monthly payment is going to take the amount you owe and divide by the months in the years you have, which is in our case 36 months. Because you make monthly payments in 3 years, because you took the car on 3 years. So in 3 years, you are going to get now divided by 36. and your monthly payment is going to be $289.96, right? So that's your monthly payment. Excellent. So now you go, whoa, way too much. Way too much. There's no way in hell I'm going to. Can you go lower? They say no problem. We can go lower. You increase the number of years for payments, and your monthly payment goes down. And is that something that right, you are willing to do? Then you say, well, how much would it be in that case? Well, guys, you have to recompute the whole problem, right? Because now this number is 5, right? And when that number is 5, this number here will change to 60, which will lower this value. But it will do something else at the same time. It will increase this value. And in this case, if you want to look at it that way, it's a win-win-win situation. It's a 3-way win, right? Dealership has nothing to do with money. When you set up a bank payment, dealership is paid in full on a spot. So they're getting their $8,000 for the car. Government is getting all the fees, and the bank is getting all the interest. That's the way it goes, right? So dealership is happy that they sold the car, they made money so they can feed their kids. Bank is happy because they made money from interest, they can feed their kids. You have the car to go to work, make money, feed your kids, so that's a three-way win, right? But increasing 3 to 5 will make you pay more for the base price while paying less every month. Now, that doesn't make sense when I say it that way, pay more because you're paying less. But you have to understand that instead of 36 months, now you're making 60-month payments. So obviously you will pay much more into it. Now, if I redo this calculation real quick, because you can literally, if you are careful with parentheses, you can stick all of this into one shot. So you have to borrow 9260, open parenthesis 1 plus 0.04 divided by 12, raised to the 60. So now, see, if you do the 5 month, you owe $11,306. That's $900 more, right, for you. That $900 will, over time, get out of your pocket into this payment plan. But now when I divide that by 60, your payment goes down to $188.44 a month. So they're able to knock off $100 off of your payment, monthly payment, if you are willing to, instead of paying back 3 years, to pay back 5 years. So same deal when you replace with the 5. I hope you will redo calculation just for your own sanity, and all of these things, right, that I mentioned, you see that they actually all work exactly as I said, right? The price of the car will go up, and very good, Paul, there it is, 188.44, excellent. And you are getting your price, the monthly price, knocked off $100, right? And the bank is obviously going to collect more interest, because now instead of making about $800, they are going to make almost double, right? So bank wins, dealership wins obviously because they sold the car, and you win in some sense, right? Because you first you have the car, second you have your payment $100 lower. Now you are the only one who has a little bit of bad as well, because you will be paying $900 more out of your pocket. but it happens over extra 2 years of payments. So it's spread out and you have more time to make more money. So when they offer you different payment plan with more years, that necessarily means that you will go and actually spend more money over time, but you will have a lower monthly payment. Now, this class and this section doesn't deal with mortgages because mortgages are not the same as these loans. See, for mortgages, you first are paying insane amount of money into interest, and then you start paying back for the actual house. So what's happening here is that and we have seen, going through 2 recessions, right? That the housing market, right, could or could not be the good investment. It depends on which way, right? I had the neighbors who bought for 305 and had to settle and sell for 372. They lost money, right? But I also know others that, sell a house and then they buy 3 houses somewhere else, right? So it's the time, right? Mostly what I'm concerned about, and this is what most people don't know, the loss of money for what I call the refinance scam. And I call it a refinance scam because that's what it is. There is only one way to refinance your house, and that is to refinance from 30 to a 15-year. Your monthly payment has to go up in order for you to refinance and save money. Pretty much in every case, every scenario that I looked at for refinancing, if your monthly payment went down per month, even when your percent goes down per month, for the loan, you are still losing insane amount of money. And that's, because at one point I was thinking about refinancing, right? And then I looked at the terms and I said, this makes no sense. Yes, I am going to have my home payment to be $300 less. It was maybe like $300, almost $350 less. But then when I crunched the numbers, I was about to lose $80,000 over the whole deal. That was insane, right? Because they wanted me to refinance my house and then just, go ahead and lower my monthly payment for, advertised $350, for about $350, and, save a lot of money. I said, yeah, but, all of the years of interest that I paid in, I'm just restarting the loan. I literally paid by that time, in a couple of years, I paid just a few thousand into the principal for the house, and nearly $80,000 went into the interest payments. So house loans, mortgages, are structured differently, and we cannot use this mathematics that we learn in this section to work those out. It works to refinance the car and figure out the way to cut around it, yeah, but not for the house. For the house, you are refinancing from 30 to 15. You are increasing your monthly spending, and that's the way when the bank is actually going to lose money. And you are going to save money. But if you are refinancing a house onto a lower payment, that's a minimum of 50,000 loss on that's the minimum, and above, right? And above. So obviously the more expensive the house is, right? I'm talking about, generally houses are like 300, like a question asked, about 300K. So you have to be very, very careful with this, because they first make you pay into interest and then you get to pay the principal and the rest. Any kind of loan student loans, and if you just go to the store, you want to buy a new computer or something, right? You swipe the credit card. What I just showed you for the car is it's the thing. You want to buy $800 computer. You add 7% to it for the tax. Usually there are no fees to pay for it, right? I mean, if you're buying it maybe online, you will have maybe shipping and handling, but that's gonna increase maybe $50, whatever, 15 or 50, I don't know, depending on what. 5,000 shipping and handling if you're buying from Apple. It's completely justified. So there you go. All right, cool. So this was the money problem, and any type of a loan, right, is going to be dealt with this way. As I said, not the mortgage. So I am not going to go into mortgages because they do not use exponential models, and but I do encourage you to look it up, right, and educate yourself before you go and make any kind of mistakes on that part. It's very easy to lose a lot of money, and it's not going to look like you lost money, but yeah, you lose a lot. All right, so now we are going to move away from money. We're done with money, and we are going to jump and look into another growth, right? So this was money growing. This was a growth problem, right? Because the money, actually, hold on. Let's just calculate the max payment. Much faster to compute, right? Max payment. Remember our principle was 9260. We were at 4% and 3 years. So when I run the E equation, it will give me a larger number than this. But no matter what compounding you use, whether it's monthly, yearly, daily, hourly, it is not going to exceed this amount. This is going to be absolutely maximum payment that you can possibly have at borrowing $9,260 and 4% for 3 years. You can't have more than that. So you can compute this by 9260 times e to the 0.04 times 3. You stick all of that in your abacus. 92 times e raised to the 0.12. I messed something up. Hold on. Oh, this is supposed to be e. Why didn't catch it? There we go. And we are getting, from this calculation, 10,440.62. And now when I divide that by 36 for monthly payment, I take 10,440.62 divided by 36 payments to get 290.02. So you see that, right? It literally added 6 cents to tell you that, right? That's the maximum that you can. Now, compound daily, compound hourly, and stuff like that would be in between these two numbers, obviously, right? And compound yearly would be a little bit below. But they're all going to go between 280 and 290. They're all going to be in that range. Now, I don't really think that you want to compound daily because then you have to make daily payments. I don't think you want to compound hourly because you have to make hourly payments. That's 24 payments per day, right? So it's not practical. But it's kind of cool to figure out this absolute maximum. And it's much faster to compute than messing with the formula above. And then you know that you're just going to pay few cents less. So you can calculate right, if you want to 5 years, you just stick a 5 in there and then divide by 60 over here. And that's going to work out to be, 188.5 5 probably, or something like that. So it's not gonna go far from where it was, just a couple of cents either way. All right, I think now we beat money to death. Oh, actually, one thing I'm just gonna quickly mention. If you don't make the payments, they repossess the car, just like they repossess the house in a foreclosure and so on. If you're not paying your student loans, you go to prison because they can't really repossess the knowledge you have. So there is that. You can't go bankrupt on the student loans. It's something that you should know, and why you should be involved with clubs and organizations to earn those scholarships moving forward. Anyway, these problems were growth problems because the money grew from 9,000 to 10,000 to 11,000, right? So the numbers are growing, therefore, right, we call them the growth problems. Another growth problem would be a population problem. And that's for biology, obviously, right? So we had our finances first. Now we're going to talk bio. Remember, we still have engineering, we have environmental sciences, we have medical field, we have all of these fields, the history and anthropology, archaeology, all of that stuff is going to be in these lectures. We just need to get there. So, population problem. Yes, we are living now in crazy times, and yes, 250,000 died so far from the virus. Let me just check. I do have a web app that it's counting that stuff. So let me just quickly refresh this abysmal thing. And I thought it was 250,000, right? Did I? Oh, it's less than 200,000. Well, I must have looked at the wrong number then. All right. So, generally what I do is I go to a website called World Population Clock. Which is not the world, just the population clock. Population clock. And you will find the first website in Google says census.gov. It's the official numbers, right? Because it's a government website. It's a census bureau, right? And they do this. So even though almost 200,000 people died worldwide from this virus, and probably it's way more because I don't think that some of the countries are reporting accurate data. The population is still growing, and it's growing really, really quickly, right? So we are now at 7.644 billion, right, today. United States is 330 million population, and it's third largest country in the world, followed by Indonesia, Pakistan, Argentina, Brazil, Bangladesh, Russia, and then Mexico overtook Japan 2 years ago. And as Japan is having huge issues with population because actually they're dying out. They're not having babies. So this is what we have now for the world population. So in the world, we have 7.64 billion population. And even if you want to say that 250,000 is the accurate number or 500,000, I would accept anything, right? It's not making any dent in this number whatsoever in terms of the corona deaths so far. So that's the world population. And I'm going to say that's in 2020 right now. Now, what I'm going to do is I'm going to jump into Google website here and look for population, the world population in whatever year before. World population 1990, whatever. So world population in 1990 was 5.28 billion in 1990, just 30 years ago. And let's say we're interested in what's the population going to be in 2030, let's say, right? This is the power of mathematics. You look at the data from the past, you create the best possible model, mathematical model that you can, which is what they use also to predict the number of deaths from the virus and so on. So you use that, and then you can predict the future, right? But you also need to be able to understand the model and see if it's a good model or a bad model, which we will have some glimpse at as we go on. So this is the problem that we can actually solve, and this is a word problem. Population today is 7.64 billion. Population in 1990 was 5.28 billion. What will be, what is the forecast population for 2030 or, 2050, or you can pick anything. So how would we do something like this? It's going to have two separate calculations because we have to figure out what K is. We don't have K calculated in here. So, first of all, my population model would be P of t is equal to P0 e to the k, P0 e to the kt. So this is the population. This is the initial population. And the k is the constant of population growth. And it's bigger than 0 because the population is growing. If the population is decreasing, then it's negative, right? T is time in years. Oh, time in years. I will one more time draw your attention to y equal a e to the kt, kx, whatever. The same equation is just, as I said, we put a different dress on it. We put p's for population, a and p for money, for principal and amount. Later on, we'll use m for mass, and so on. All right. The first order of business is to get P0 and K. To compute what we must. I don't know how to say that. Do this. That's the step number 2. Right? So get P0 and K. That's the first step, because that one gives us mathematical model. Maybe I should just say answer the question. How about that? We just say answer the question. There we go. Answer the question. Worldometers. I'm not sure what the worldometers is. I'm using census.gov for population clock. I was my screen was switched away from the chat, so I missed a couple of these messages. But yeah. All right, so let's go and deal with this. I am going to start in 1990 like nothing existed before. I'm going to set t equals 0 in 1990. All right? So, as far as this problem is concerned, that's the Big Bang, right? The population clock starts in 1990, and that's why the value that is given of 5.28 is going to be our P0. So we are going to start our clock at 1990, and we're going to set the clock at 0, and that's our starting point, which is why we are able to say initial population. We don't care what happened before. That's our starting point. Okay. That already gave me P0, which is awesome. And then I will say 30 years later in 2020, when t is 30 years later, we have the population to be 7.64 billion. So what I have here is enough information to calculate k. You must have 2 points in time to compute k. So we are going to now say that our problem P of t is equal to P0 is 5.28 e to the kt. Right, so this is the formula, and look what I have. I have t and p to plug in. Once I plug those values in, I can calculate k. It will be the only unknown. So plug in, and we get 7.64 is equal to 5.28 e to the 30k. Right, it's k times 30. Right, t is 30. So just write it as 30k. And now divide both sides by 5.28. So 7.64 divided by 5.28 is going to give me, right, when I divide both sides by 5.28, I'm going to get 1.4469, so that's going to be 70. Well, I could just put 7. Is equal to e to the 30k. Now we know that e is undone by ln, so I'm going to apply ln to both sides. That will kill off that e. So I have ln of the answer, which is the 1.447. It's going to give me 0.3695, again 4 decimals, is equal to 30k, because ln killed off e. And now I just divide previous number divide by 30 to get that k is equal to 0.01232, because the next digit is 5, so it will round it up. I got k. So P of t is equal to 5.28 e to the 0.01232 t. This thing is called mathematical model for population since 1990, because that's where we started. So what you see here done in black is all step 1 to get k and p0. And now I can answer the question, which is, what is the population in, what did I ask for? Population in 2030. So 2030 is t equals 40. So we need to calculate P of 40. You just plug it in. So 5.28 e to the 0.01232 times 40. You punch this into calculator in one shot. 5.28 times e raised to the open parenthesis 0.01232 times 40. And I get 8.64 billion by this model. So we are expecting population, right, to jump from the current population, right, that is 7.64 to 8.64. So we should add 1 billion people to the population of the planet in the next 10 years, right? At the rate, exponential rate at which we are growing population right now. Now someone would say, no, that sounds insane to put in 1 billion people on the planet in 10 years. No. We doubled the population of this planet since 1970. I believe that I'm going to now real quick check the population in 1970. 3.68. 1975 is already 4. 72. Perfect. There you go. So 1972 was when we had half of the population than what we have today, right? So those 48 years added 3.8 billion people. Now, you have heard expression before, who has money makes money, right? Which means if you have more of something, an exponential growth, it will grow very quickly. Now, a lot of people don't understand exponential growth. And usually I have this, I do this dramatic in class and everyone is guessing and a whole lot of people are wrong and it's really funny. Now I just get to show it and it's kind of bland, but such is life. So if you have a dish of some kind and you put one bacteria on the bottom at 00 a.m., right? So you are looking at midnight. and at 12 a.m. noon, right, will be full. Because bacteria splits into two, but it splits every minute. The question is, at what time the glass or the jar or whatever will be half full? That's the question, right? So we are starting at midnight. A lab researcher or whatever, right, places a single bacteria that splits into two, right, every minute. So puts one at midnight and walks away, comes back at noon, 12 hours later, and the dish is full. At what time you had half? All of you who said, well, clearly at 6 a.m., you are wrong. Not at 6. It's at 11:59 was half full. At 11:59. Why? Because think about it, right? If it's full at 12 and every bacteria splits, so minute before the end, every bacteria split in two. So you had to have at 11:59 the bottom filled with bacteria, and then when each of those bacteria in the lower half splits into two bacteria, it just fills up the second half, and you have the full dish. Right now, there's a growth period and all that kind of stuff, but we're going to ignore that. So that's exponential growth, and we are experiencing it now because we just learned that we are going to add 1 billion people, right, in next 10 years. Well, why? Because there is already 7.6 billion, and 7.6 billion can multiply into another billion over 10 years, right? So you say, well, we'll just find another planet. Overpopulation is not an issue because we just find another planet and we move, right? We colonize Mars. Let's go, Musk. Hop, hop. Let's go, right? Get that technology up and running. It's not going to help. It's not going to help because if you find another jar, which is another planet, that one is full at 12:01, because this one over here is full, and when every single one splits, it fills the second jar instantly the next minute. And when you find another two jars, these two will be full at 12:02. See, just 1 minute. This is called exponential growth. This is why you heard, oh, grows exponentially. Even the people that don't understand what it means, exponential growth, they still use it because they just know it's a lot. Well, there it is, right? You see that it grows 1 minute from 11:59 to 12 o'clock. 1 minute, it fills the first jar by half. And then you bring in another jar. The next minute, the second jar is full because every bacteria from the first jar splits into two, and each pair goes into the second jar. Now you have two jars that are full. At 12:01, you have two full jars. Well, next minute, the first jar duplicates itself, and the second jar duplicates itself. So you need two jars to contain the extra amount. Then you need 4 jars, and then you need 8 jars, right? It never stops, right? The population explosion, right? It's exponential problem. But now, is our model good? And obviously, no, right? Because there are no other jars. Our technology is so pathetic We as a species are so primitive that we are stuck on this planet with no means and no hope of going anywhere. Right? We are type 0 civilization. Type 0. Still. So the flashy cell phones and, the computers and me talking over the, wireless internet and all that stuff, that's nothing. All right? It's laughable. Some people say, why we are not visited by aliens? Why? Like, you don't go out of your way to visit an ant colony because you can care less. Well, ants are way more interesting to us than what we would be to advanced alien civilization that has been around for quite some time and developed something. We literally as a species have nothing to offer. That's how pathetic we are, actually, when you think about it. Like, think about how long it takes you to go anywhere in your car, and we have a speed limit of 65 miles per hour on a highway. Go to Pennsylvania, it's 50. It's even more pathetic, right? Then you think you can't be more pathetic than 65? Just go to Pennsylvania and you find the more pathetic state, right? So there you go, right? So when you think, or New York also has highways at 50 miles per hour. So that's another pathetic state. So when you think about this, right, and then you try to see on a cosmic level, like, how fast would the planet be going around the sun? Just as a point of reference, this is the average calculation. If you are to take your car and drive 60 miles per hour on the orbit of the planet around the sun, so if there was a highway or the orbit that the planet, right, the way that the planet takes around the sun, and you drive 60 miles per hour there, it will take you 1,111 years to go once around the sun. Planet does it in 1 year. And if you're driving 60 miles per hour, it will take you 1,000 years to go around. This is how pathetic 60 miles per hour is. That you just need to understand how pathetic we are as a species. How insignificant we are to anything, right? So, on a cosmic level. So, looking at that, right? Finding other planets, finding other jars is not going to be fun, right? The closest stuff is 10,000 light years away, which means that you have to travel 10,000 years at the speed of light to get to the first place that has nothing. So that's just a little bit of order of magnitude of where we stand as a species, right? So finding other jars is out of the question. Terraforming poisonous Mars, that it's third size of the Earth with the gravity as weak as possible and so on, is, it's nice to have an outpost, right? But to make it livable? Nah. Poisonous ground and poisonous atmosphere, everything's poisonous to us over there. So good luck with terraforming that one, right? So now what we learned is that our population function doesn't really fit. Doesn't really fit because its graph looks like this. You are going to start counting somewhere. That will be your initial population. I don't care if it's 1990, or you can go to year 0, or you can go to year negative 3000. I don't care, right? You start counting somewhere. You see what the problem is? The end behavior over here is going to grow to infinity. Well, what is this suggesting? It's suggesting that we are going to it's suggesting that we are going to grow our population all the way to infinity, on a planet that has a finite surface, finite resources? And obviously the answer is hell no, right? We cannot do that. We cannot get our population to be growing infinitely, right? Because eventually we are going to run out of the habitable area to build houses, farmable land to make food, dig all of the resources in terms of coal and oil, which is another testament of how pathetic we are as a species. We still run most of our technology on exploding or burning ancient plants and animals. So look up what oil is, what coal is. Look it up, right? If you don't know what those resources are, and understand that most of our electricity is produced from coal, and understand that most of our cars are running on gas that it's product of oil, and understand how pathetic we are, right? We are literally digging up 100,000-year-old carcasses, exploding them to go from point A to point B at 60 miles per hour. All right. Depressing, but true. So we see that this model is not good. It's good on a short run. The 1 billion calculation is probably good, but don't ask me what's going to happen in the year 3000, because that's definitely going to be off. Now, why do I know for a fact that if I use this model to calculate year 3000, everything is going to be wrong? Well, there is something that the scientists call carrying capacity of the planet, which is the maximum amount of population of people that this planet can sustain. Going over that number, we are going to be short on all kinds of resources, which is where people who stocked on guns are going to start campaigning for resources, obviously, right? So we all know what happens. When you can't get to the food, when you don't have enough farmable land, when you don't have, right, because there's just way too many people. Now, scientists can't agree. Is that going to be 9 billion, 10 billion, 12 billion, 15? The highest number I've ever heard was 15.2. That's the highest number I've ever heard. The lowest number I've ever heard was 9 billion. Great, we're going to be there in 15 years. All right? At this rate. Exponential rate to growth, right? So, the population is a huge issue. And we see that this exponential mathematical model doesn't really fit very well, because the planet has the finite size and we can't fit infinite people on a finite size. So there has to be a different formula which deals with this, and there is. That formula is called logistic growth model. The book will tell you that the logistics growth model is given by f of t is equal to c over 1 plus a e to the negative bt. But when you go into Calculus 2 differential equations, if you are interested in these things, you are going to get a formula that is way better than that. I'm going to show you that formula without writing it here. Obviously, if you guys are interested, you will pause the video, write it, and jump there. So here are the population models. We deal first with the one, and we say it's garbage one, and then this is just talk, and then here it is, logistic equation, and then we go through all of these calculations to come up with this thing here. Now, if you look very carefully at this equation, it has the form of the equation I just gave you, right? 1 plus, in a denominator, 1 plus a. So imagine you're dividing all of this with p0. P0 would cancel on top. You would get a 1 on the bottom. And then all of this m minus p0 over p0 would be that a, right? That it's in front of e. So it's very easy to convert this formula into the formula that you see in your equation. Why am I showing you this formula? I am showing you for one particular value, and that's this m. That's the only reason why I am here. This m is called carrying capacity. And that's the carrying capacity we talked about in our 2 seconds ago, when I say that there is a maximum amount of people that the planet can sustain. So, when you see the graph of logistics model in the book, it's going to have this horizontal asymptote, and that's going to be that m you guys saw in that equation over there. And you are going to have some initial population p0. It's going to shoot exponentially, and then it's going to level off, and it's going to flatten, and it's going to follow the asymptote, because it has to obey the asymptote, not cross it, right, going to infinity. And as the time goes on, you never get to go over it. Now you say, well, what if we spike over it? Well, the quick little war will bring the population down to the point where you have you have this. And it's a different type of the wars we have so far, right? The wars we have so far are the wars because of misunderstanding, right? Or even dumber things like religion and stuff like that. But in terms of the carrying capacity of the planet, that's the war for resources, right? That's a different kind of a war than what we had, because it's literally there to just decrease the population, because that's what the nature always pushes down to follow what has to be followed, right? So there is the carrying capacity. And now when you look at this model, right, scientists are trying to figure out what is this m. Is it 9? Is it 10? Is it 12? Is it 15? Or maybe 13.7? Right? They are trying to figure it out for years and decades now, right? To come up. And everyone has their own reason why and how, right? Their number is the best number out there. But all the numbers that I've heard were from 9 through 15.2 was the highest I've ever heard. So that's the thing. And what else is cool about this logistic model here is that it's the same one that is used for many other applications, which includes also coronavirus. If you are looking at this particular graph, there is the carrying capacity, which is maximum amount of people that could get infected and possibly die from it. And that's not going to be the population of the planet. As a species, we went through many plagues and many pandemics and many of these issues. My parents' generation was freaked out about polio. Many of you don't know what polio is, right? I've been part of Rotary. We are eradicating polio. There are only 3 countries left in which polio exists, and one of the 3 strains of polio is eradicated. Some diseases can be eradicated if you aggressively, and if you give a lot of money into it, right? You can eradicate disease. But every generation of people had this boogeyman, right, of disease or a plague or something, pandemic, that killed a lot, but never killed everyone, right? We also have socialist regimes, right? that killed more than anything, right? Nazis, that's socialism. Stalin, that's socialism, right? So you have that as well. In China, right? The hundreds of millions of people dead, right? From socialism. So there you go. You have all of those, right? And when you look at the population, it's not everyone died. So coronavirus, as scary as it could be, it's not going to kill everyone. Now, by now, you might know someone who has, and I know quite a few people who had it with various, right? And I only know of 2 people who died, right? But I know, I believe, 7 who had it and didn't die at this point. So what's today is 4/22, right? 4/22. I am personally know of 2 people who died due to corona. So none of the public TV announcements and stuff like that. Like, I don't know any of those people, right? I'm talking about the people that I would know. 2 that died and 7 who definitely had it confirmed by a test and did not die. Now, 1 person coughed 2 days. Didn't even know. Didn't even know they had the virus until his wife ended up in a hospital with a fever for 5 days, right? And then he tested and he said, "Oh, I had no clue that I'm dragging corona, right, 2 weeks." So this is what's happening. Same thing is happening with HIV, right? You have people that carry HIV, do not get sick, do not die, spread it and give it to everyone else, right? So some people are just naturally immune, and that disease will do nothing to them even if they carry it, even if they spread it. So if you are looking at this graph, and P now is the population of death, right? This is, if you want to take a look at this as a death graph, then there is a maximum amount of people that could possibly die from this. So if they say that the rate of infection is so and so, and the rate of death is 20% within the rate of infection, then that's the percent that you can take off from the whole population of the earth. And you will see that population-wise, it's not going to make a big dent at all, right? Now, I don't know what the infection rate is, but the death rate is about 20 to 21%. That's where it fluctuates, right? So whatever the percent is for the infection times the percent for the death, and then there will be the percent of death. And then you take that percent off of the whole population of the planet, and corona cannot kill more than that. But it's not even guaranteed to kill that many, because isolation and quarantine and, people might be living secluded, ones that are susceptible to it might be living and being so secluded from others that, the virus will never reach them, even though they might die within 2 days of it, right? So this logistics, right, can also be used to trace computer virus spread, right? In the old days, right, when Windows was full of holes. Well, and not just Windows is full of holes. I mean, it's enterprise equipment that companies use, so a lot of people will be writing viruses for it. That's another thing. They say, oh, buy a Mac because, they're resistant to viruses. No, they're not resistant to viruses at all. It's just that no one is wasting their time to write viruses for the computers they have nothing to steal from. When you are writing viruses for Microsoft products, it's enterprise right? The companies are using that. So stealing some company secrets and selling them on the black market earns you millions of dollars, where what you're going to steal off of a personal checking account, $300 to $3,000, like it's nothing. So no one wastes time writing Mac viruses because there is nothing to steal. If those computers were any good, then they would be used in enterprise setting. In that case, there will be as many or more viruses than what you have for Windows machines. But in the other rate, there is a set amount of circumstances looking at the protection and the network configuration and level, user level and all of that stuff. There is, again, the certain level of computers that can be infected with the virus. And then you will never have a virus that can affect all of the computers, or a human virus that can affect all of the humans. That doesn't happen. Otherwise, as a species, we would be gone long time ago. Funny thing, when the plague was going on in 1600s in Europe, and when there was a quarantine, self-imposed quarantine and separation and everything, right, that is happening right now, Isaac Newton went to the village and invented calculus. Okay, so just a little side note of what happens in quarantine when you have people that, right, have no internet connection. All right, so that's one of them. All right, the last formula that I want to talk about tonight, have a few more minutes here, is the Newton's law of cooling, since I mentioned his name. And next class, in a part 2 of this lecture, it's always 2 parts, we will deal with decay, which will give us history and environmental sciences and medical stuff, right? So we'll deal with that. So Newton's law of cooling. Is great because you can use it to compute the time it will take you to, I don't know, bake a cake, bake a chicken, do a turkey for Thanksgiving, right? So, and I did this many times. Measure the temperature of the chicken or the turkey or something, stuff it in the oven, wait 30 minutes, take it out, measure the temperature, put it back in, use that temperature to calculate the time, set the timer, forget about it. When I take it out, perfect, because it's a mathematical model. Formula is T equals C plus T0 minus C e to the KT. T is the temperature. C is the room temperature. T0 is initial temperature. T is the time. Define minutes or hours. But you have to be consistent, right? And K is just a coefficient, right? It's just a constant. It actually represents what type of oven you have, the size of the thing you are cooking, the whole bit. Now, Newton's law of cooling can be for heating and for cooling, depending on whether K is positive or K is negative. So the what I want to say. So you can use this to also calculate how long you need to wait for, coffee to cool down to a certain degree and so on. So there's a lot of application for this. And, some of my calculus students, differential equation students, for their project, they would get to bake a chicken or a cake or something, right? To do do the report, do all the calculations on the side. Differential equations have to derive the equations and so on. But being that we're in this lame semester when there are no projects, anyway, can't do anything cool now. So let's bake a chicken real quick. So to bake a chicken, right, we are going to have this chicken initially at 70 degrees because it was sitting on a counter. We are going to put the chicken in a room called the oven, and the room temperature there is 400 degrees. That's the room in which the chicken is going to be for some time. We are going to look for the target temperature of 165 degrees, because that's when the chicken is thoroughly cooked. You don't want to go below that one because salmonella and other stuff that ancient people didn't know about. We're going to do time in minutes. We can also do it in hours, but time in minutes is just fine. And we can go and start baking. But here is the one thing that you have to do. Say 30 minutes into baking, we take the temperature of the chicken. So 30 you put so your oven is heated at 400. You put the chicken in, and that's when the timer starts measuring time. That's the 0 time, right? Initial temperature of the chicken going into the oven is 70 degrees, and you have a 400 Celsius, a 400 Fahrenheit room temperature, because that's the room chicken is in, right? Called the oven. So 30 minutes into the baking, you take the chicken out of the oven, you stick that thermometer in, and you measure that the temperature of the chicken is, let's say, now 87 degrees, whatever. This is the piece of information, 3087, that we have to know to calculate K. Because K, as I said, is the constant that mushes a lot of different things inside. Type of the oven, gas, electric, wood burning, right? Size of the chicken, right? It's a small, medium, large. Container chicken is in, right? Because the heat penetrates differently. If it's lower walls, higher walls, metal walls, aluminum walls, right? It's just, or the glass thing, or a ceramic, right? So they all have different properties. When all of those factors, right, mush together, they will make chicken bake longer or chicken bake faster, right? Longer or shorter. And we need to know that K. Now again, it's not supplied by the manufacturer of the oven, because the oven manufacturer doesn't restrict you what dish you're going to use or how big the chicken is. There's a lot of other, right, other than the temperature of the oven and the type of the oven. There's a lot of other factors. So all of those other extra factors that they can't control is mushed into this K in this calculation. And that's why we have to do this measurement to come up with this extra point. By the way, this point is equivalent to your 1990 population point, because it was exactly used to calculate K, if you remember that. All right, cool. Just plug all of this mess in to calculate K, and then redo the calculation to figure out what time, right, you need. So, quickly to plug all of this in, I'll write the formula one more time over here. temperature is equal to the room temperature plus T0 minus the room temperature times e to the kT. And we plug all of our values in. Remember, we measured the chicken was at 87 degrees. The room temperature for the chicken is 400 degrees. The initial temperature for the chicken was 70 degrees. Minus the room temperature is 400 degrees. E to the 30 minutes times K. Can you do this in hours? Yeah, it's just going to be 0.5. But it's always annoying to convert hours and minutes into the decimal scale, because decimal scale is off the 100 and the minutes are off of 60. So there is a conversion factor there. So it's just better to do it in minutes, And we can just throw away seconds if we get any decimals with it. Just keep the round minutes. All right, so if you take a look at this equation, it's exponential equation with only one variable. We'll have to use ln to dig that variable, but So we have 87 minus 400 is equal to 70 minus 400 is negative 330, e to the 30k. Over here we have negative 313 equals to negative 330 e to the 30k. Divide both sides by negative 330. And we get positive, right? So 313 divided by 330 is 0.9485 is equal to leave some space e to the 30k. Hit both sides by ln to kill the e. So now we have ln of the answer. Gives us negative 0.0528, and then should be 8 again, but it's a 9 because of the next digit, equals to 30k. And finally, k is equal to, divide this by 30, negative 1763. 1763, yes, when you round to 4 decimal. Finally, we have our model. I have that the temperature is equal to C plus T0 minus C e to the negative 0.001763 T. And now you can just redo your calculation. Your target temperature is 165. So this is what we want. Let's put the need for health reasons, all right? So this is what we need. We know that the oven temperature is 400. We know that the initial temperature for the chicken was 70 going in, minus 400. And now e to the 0.001763 T. So I hope you see that the T is the only variable, and it's the same calculation as before. Right? So we have negative 235 is equal to negative 330 e to the negative 0.0017 kilometer 3 T. Divide both sides by 330. So 235 by the 330. So we get 0.71212 equals leave space e to the negative 0.001763 T. Hit both sides by ln to kill e. because they're inverses. ln of the answer is negative 0.3395 equals to negative 0.001763t. Divide the number you got by 0.001763 to get t equals 192.6 minutes. So bake 193 minutes. Now remember, you already had 30 minutes, right? So you do this calculation after you check after those 30 minutes. So you will subtract 30 to see how much more time at that point, right, would be 160. So about 2.5 hours. But bake, how about we say total bake time? Total bake time, 193 minutes. That's 3 hours and 13 minutes. Now you already baked 30, and let's say it took you some time to do this calculation, right? So you take away 40 minutes from this time and you set the timer, right? You can time yourself how long would it take you to run through the calculation. Because you can't start the calculation until you have the data point, right? Because you need this data point to calculate K. And so that means that you already waited 30 minutes into baking, and let's say it takes you 10 minutes to compute this. That means it took you 40 minutes, right, for the data point and 10 minutes to calculation. So you will take away 40 minutes from here and set the rest, right? So 153 minutes on your timer. Just walk away. You put the cell phone alarm, you have the timer on the oven, and you just walk away. When you take the chicken out, right, if you did all the calculations correctly, it's a very cheap experiment. You can buy a whole chicken for $5, right? And if you're vegetarian, buy 2, because I'll eat them both. Just, go from there. It can be done on cakes and stuff, but generally we don't poke cake with a temperature probe, right? It's usually some meat that is being prepared. So these are the growth problems, right? These are the growth problems. We've just seen the growth in temperature from initial chicken being at 70 to growing the temperature to 165. We have seen the growth in population. We have seen the growth in money, right? Because you borrow money and then it grows into what you owe because of the interest. All of these are growth problems. And what we are going to do on Monday are decay problems, which will end chapter 3. At which point we could have, this I'm just saying could have, review on Wednesday and exam that weekend, or we can push exam for next week, but that's the last week, which means the following week you will have final. So including final 3 weeks left, and you will have the choice of having your exam 3 on either the weekend of May 1st or the May 8th. That's the choice. We must have exam 3 then. And then the next week is the week of the finals, when we must end the course. On the 18th, we are starting summer. That's it. Summer 1 also all online. If you are signing up for courses, you should do that as soon as possible, because online classes have less people than the face-to-face classes. So some sections that had 30 people will now have 20 people in the online section, so they open a new section for those other 10 people. So you might have been moved from the class you wanted and a professor you wanted. I mean, just professor, right? Into a section that is taught by a different professor because of the caps for online teaching. It's way too much work. It takes a long time to grade these online exams and things like that. So my hope is to post your grades for exam 2 sometime this weekend, Saturday or Sunday. So there will be an announcement for it. But, think about that. Is there chapter 7? Yes, there is chapter 7 in order for you to learn systems of equations. So 7.1 you already know. Solving systems 2 by 2. We only need to learn 3 by 3 systems and some of the non-linear stuff so you can survive your Precalc 2 and later on, especially Calc 3. I know not everyone is going to Calc 3, but math is always building up, and these concepts are pre-calculus concepts. So there will be chapter 7. And if I have to add another class on, let's say, Friday at 1 or something like this to teach an extra lecture, so be it. It's not a big deal. And office hours will be held. Obviously, if you have any questions, just email me and we'll get together. So we are almost done with chapter 3. So Monday will be done chapter 3. On Wednesday, depending on when you want your test, Wednesday is either going to be review or Wednesday is going to be the 7.1 and 7.2. So we'll see. That's it. We went over time, but we had fun. And Monday's class is going to be way more fun than this. This one was grim about population, overpopulation, coronavirus, and all these kind of things. Next one will be grimmer but fun. So see you on Monday on YouTube. Bye.